So now you want to test for equal means between more than just two populations. Let's say, for instance, that you're given 3 sample datasets, and you need to figure out whether they come from underlying populations that share the same mean. Now, just to be clear, the populations themselves don't have to be equal, they just need to have identical means. Let's say, for example, that you're given 3 sample datasets, each containing IQ scores, but of people with a different eye color. Now, to investigate the questionable hypothesis whether indeed people with different eye color will have on average a different IQ, you need to figure out if these 3 sample datasets come from underlying populations with a different average or a different mean. And therefore, you need to perform a statistical test. Now, you could be clever and perform the corresponding t-test for equal means pairwise, meaning between each pair of 2 datasets. For instance, between brown and blue, blue and green, and then green and brown. Now, that would indeed give you a conclusive answer. But if the number of sample datasets increases, the number of tests that you will need to perform also quickly increases. Instead, the better option to compare means between multiple samples is the ANOVA test, which stands for the analysis of variance. And as was the case for the previous test that we looked at, also the ANOVA test comes with some requirements on the underlying datasets. In this case, equal variances and roughly normalcy. But it turns out that the ANOVA test is quite robust under these requirements. So let's now look at what the ANOVA test actually does, because its name, analysis of variances, is quite confusing, given that we're looking at statistical tests that tests for equal means. So why this name then? Well, because in order to test for equal means, it looks at 2 different types of variances in our datasets. In fact, it compares the within variance with the between variance. So what are these 2 variances? The within variance is the familiar one. It is just the variance of each of our 3 sample sets. So it's a measure for the spread of data points within each sample around the sample mean. Now, these within variances, which for our example are 3 numbers, are compared to the between variance. Now, for the between variance, we first compute the overall mean of our entire dataset. To get the between variance, we first compute the overall mean. This is the mean of all of the data points across our 3 datasets. And then we look at the spread of our sample means, which in our case are 3 numbers, and this spread can be quantified again as a variance, and this will be the between variance. And then the test statistic for the ANOVA test is proportional to the ratio between these 2 variances. And then for the test itself, the same logic as always applies. This ratio between variances is distributed according to a known distribution if the null hypothesis is true, meaning if all of the underlying populations indeed share the same mean. Therefore, if we compare our specific test statistic computed for our sample sets and we find a very extreme value compared to this distribution, then we reject the null hypothesis. And we can conclude that at least one of our underlying populations does not have an equal mean. Now, because this still might sound quite abstract, I made a visualization that shows what the ANOVA test roughly does. So what do we see on this figure? Well, first of all of the data of our 3 sample datasets is visualized on this figure. For each sample, all of the data points are visualized as a scatter plot along a line, and each in its own color. Sample 1 will be blue, sample 2 will be green, and sample 3 is purple. Now, for each data set, we compute the sample mean, and then we visualize it as a horizontal line across the scatter plot. Blue for sample 1, green for sample 2, and purple for sample 3. Then to visualize the within variance, meaning the spread of data around each sample mean, we first compute the variance of each sample set, and then use this variance to make these shaded boxes. Now, these shaded boxes, as before, contain all of the data points that lie within 1 standard deviation from this sample mean. And by now we know that roughly 70% of all of the data thus lies in this box. Now this is true for sample 1, for sample 2, and for sample 3. And thus at this point, we already have a visual representation of the sample means and also of the within variances. Now for the between variance, the first thing that we need to do is to compute the overall mean of all of the data points taken together. And then we visualize it as this horizontal black line. So this is the average value of all of these data points taken together. And then what the between variance quantifies is the spread of the sample means, so the colored horizontal lines, around the black horizontal line, because this is a measure for the spread of the sample means compared to this overall mean. And then what the ANOVA test does is that it compares these two variances with each other. Now, visually, this can be thought of as the following. If these colored boxes, which visually represent the within variance of each dataset, align with each other, or if these sample means align with each other, then it is very likely that these samples come from underlying populations with an equal mean. And this then will express itself that these sample means will deviate only little from this black overall mean. If, on the other hand, as is the case in this figure, these boxes do not really align, in fact, in this case, this green box seems to be the odd one out, then we reject the null hypothesis, and we can conclude that at least one of our underlying populations does not share the same mean. So let's now look at an example of these two scenarios. In the first scenario, we compute the sample means to be 1.933, 2.031, and 2.572. Now, visually, we see that these boxes very much align. And indeed, these sample means are very close to our overall mean. And indeed, if we compute the p-value for the ANOVA test, which is given here, we get 0.076. And this is indeed very small, but still larger than our statistical significance of 0.05. And thus in this case, we accept the null hypothesis that these three samples are likely to come from underlying populations with the same mean, even though we clearly see that the variance of this third sample is very different from the variance of the first two samples. The only thing that matters here is the means of the underlying populations. The other scenario is the one that we looked at before. Here, if we compute the sample means, we see that clearly sample 2 is not in line with the other two. And this can also be visually seen by the fact that whereas the boxes of sample 1 and sample 3 very much align, and their sample means are almost identical, sample 3 is clearly odd one out. And this also reflects in the p-value that we compute. It's basically 0.00 and so on. So for all intents and purposes, it is 0. So thus we reject the null hypothesis and we conclude that at least one of our three samples comes from an underlying distribution that has a significantly different mean than the others. And this brings us to one of the downsides of the ANOVA test, which is the following. If the p-value is very low, which was the case in this scenario, then we can conclude that not all underlying populations have the same mean. But, crucially, it doesn't tell us which of the underlying populations doesn't share this equal mean, or even if it's more than one that doesn't share the equal mean. And this information is simply not included in the statistical test. However, using this visualization that we made, you can clearly see which one will be the odd one out. In this case, clearly sample 2. So let's see how we can now implement these IDs and make this figure in Python code. And by now, all of the code that you will see in this cell will be very familiar to you. First of all, we define our populations. We have two normal distributions and one Rayleigh distribution. Then, from these populations, we generate three samples, one sample from each population, and each sample will have the same sample size of 50 data points. Now, because we are comparing sample means to get to population means, we of course need to compute these sample means, which is done very straightforwardly. Then the first new thing is to compute the overall mean of all of these sample data points taken together. Now we can do this by first concatenating all of our 3 samples and then taking the mean. The next step is to compute the within variances and the between variances. The within variances is very straightforward, just the variance of each sample data set. Now for the between variances, we look at the spread between our sample means and this overall mean. Now to do this, we first take the difference between our sample mean and the overall mean. We square this difference, which is done to compute the variance, and this we do for each sample. So for sample 2 and for sample 3. Now because in some scenarios, we might have samples with different sample sizes. And because we need to take this into account when we compute the between variance mean, we multiply each of these numbers with the number of sample points in the corresponding sample dataset. But in this case, each sample dataset has the same number of points, and thus this will be always the same number. And then to get the total between variance, we would take a weighted average of these 3 variances. But because here we don't use this number explicitly, we don't need to do that. And the next part of this cell is visualizing all of these elements. And the most interesting part is arguably this scatter plot, because we want to visualize all of our data points on the same visualization. However, we don't want to mix them all up. Therefore, we want to scatter plot each dataset on a different line, corresponding to a different dataset. Now to do this, we use a scatter plot, then this 1 between brackets multiplied by n sample. And then we give our sample, which of course with a corresponding color to distinguish between them. Then for each dataset, we also plot the sample mean, corresponding with a horizontal line in the corresponding color. And then these lines of code take care of our shaded areas. So we first make horizontal lines that indicate this mean plus 1 standard deviation and the mean minus 1 standard deviation. And we do this for each sample, so 2 lines for each sample. And then we fill color between these bounding lines to indicate this in-between variance. This will be the region in which all of the data points fall that fall within 1 standard deviation of our sample mean. Then the next line will be the horizontal line indicating the overall mean, which was the mean that we computed for all of these sample sets across the 3 samples taken together. Then we take care of some layout and our figure is already done. And this gives us indeed this figure that we see right here, which very nicely illustrates what the ANOVA test actually does. Now, of course, we also want some numbers, and the actual statistical testing is all done in these few lines of code. But first of all, as I said at the beginning, we need to check some requirements, namely, first the normalcy of our underlying distributions, and then the equal variance between our underlying distributions. Now remember here that our third population came from a Rayleigh distribution, so not a normal distribution. So it only makes sense to only test sample 3 with the Shapiro-Wilk test for normalcy. And then because population 1 and 2 were normal distributions where we set the variance to be equal to each other, 1.5 standard deviation, the only variance that we need to check or test is between population 2 and population 3 and see what we indeed get. If we indeed defined a population 3, a Rayleigh distribution, which has roughly an equal variance to the other 2 normal distributions. And that's, of course, we can do with the Levene's test. So we do stats.levene, sample 2, which is the normal distribution, and sample 3, which comes from the Rayleigh distribution. And then, of course, comes the statistical test for the actual means. Just for context, we first print all of these sample means, rounded to 3 decimals. And then comes the statistical test, namely the ANOVA test. So we do stats.f one way, and we give our 3 samples. And we can store this in the ANOVA test, and to get the actual p-value, we add to it .p-value. Now we round this number to 3 decimals, and we can print all of our statements. So if we run this cell and we look at our print statements, then we see the following. We see that even though our population 3 was a Rayleigh distribution, still the Shapiro-Wilk test gives us a result that population 3 is indeed normal enough, if you can say it like that. Then to check the equal variance requirement between, on the one hand, our two normal populations, where we actually fix the standard deviation to be equal, and then on the other hand, population 3, which was the Rayleigh distribution, we performed the Levene's test on sample 2 and sample 3. And there we find indeed that we have a p-value that allows us to conclude that the underlying populations indeed have a similar enough variance for this requirement to be fulfilled. And then comes the actual test between the means. So we had a sample mean of 2.553, 0.584, and 2.666. Now, clearly, this middle one is the odd one out. And correspondingly, we get a ANOVA p-value of 0.0. Now, what happened if we would set these means equal to each other? So here, we take for the second population also a mean of 2. Now we run this cell and we see what happens. Well, clearly from our figure, we already see a clear difference. But of course, this is quantified by looking at the corresponding ANOVA p-value, which is much larger than 0.05, and thus we accept the null hypothesis that the underlying populations of our three samples do indeed have the same mean.